Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack Series.
It is always wonderful to be here. This is a topic I am especially excited about.
Today we are exploring the history of celestial navigation and ancient astronomy. And, I think we have to check a bias at the door right from the start.
Oh, yeah. What's that?
Well, when I hear ancient astronomy, my mind, and I think a lot of people's minds, immediately pictures something a bit primitive. A lone sailor on a raft, squinting at the North Star, or maybe a priest in a long robe just making up stories about the constellations.
Right. It feels quaint, almost like pre-science, like they were just playing connect the dots with the stars to make pictures of bears and hunters.
Exactly. We frame it as mythology with a little bit of stargazing thrown in for flavor. But digging into this research, from the Babylonian clay tablets to, and this is wild, DNA studies of ancient Polynesian chickens, that view isn't just a little condescending, it's completely factually wrong.
Oh, it's so wrong. For these cultures we're looking at, the sky wasn't a source of romance or mythology. It was infrastructure. It was a survival mechanism of the highest order.
The sky as infrastructure.
Yeah.
I love that framing. That's the real hook, isn't it? Because no matter if it's 2026 or 2000 BCE, we all have this universal pull to just look up. We're drawn to the beauty. But for the people we're discussing, the sky wasn't this pretty passive backdrop. It was their clock, their map, their calendar, and a storybook that literally defined their reality.
And you have to remember the stakes involved. I mean, if we get the time wrong today, we're maybe late for a meeting, or we miss the beginning of a movie.
Right, it's an inconvenience.
It's an inconvenience. If the Babylonians or the Maya got their timing wrong, the crops failed and people starved. If a Polynesian navigator misread the angle of a star by a half a degree over a long voyage, the entire crew, the entire canoe dies of thirst in the middle of the Pacific.
So the margin for error was, for all intents and purposes, zero.
Absolutely zero, which is exactly why the level of mathematical precision we find in these sources is just so staggering. It's hard to believe.
We have a huge journey ahead of us today. We're going to get into how the Babylonians literally invented the concept of time that is, right now, ticking away on my watch.
It's true.
We're going to look at the Venus detectives of the Maya, the incredible brilliance of the Islamic Golden Age, and then, of course, the Pacific.
The Pacific. I have to say, the story of how Polynesian wayfinders crossed the largest ocean on Earth without a single mechanical instrument, for me, that might be the single greatest engineering feat in all of human history.
That is a bold claim. But I have to say, after reading about things like Tilapa and the octopus map, I think I'm starting to agree with you.
We'll get into all of it, and also how we finally shattered that old idea of the crystal spheres with the hard physics of Tycho Brahe and Johannes Kepler.
Okay, let's do it. Let's jump into Section 1, Foundations, what we think we know, and we have to start in Mesopotamia with the Babylonians.
The masters of the math of the sky. Absolutely.
This part of the research really stuck with me because it's something I interact with every single day, every hour, and I've never once questioned it. Why is an hour 60 minutes long? Why is a minute 60 seconds?
It seems so arbitrary, doesn't it?
Completely. We have 10 fingers, 10 toes.
Yeah.
You'd think base 10 would be the logical default for everything.
Well, it feels arbitrary to us, but it was a very deliberate choice for them. This is the legacy of the Sumerian and Babylonian sexagesimal system, a base 60 system.
Sexagesimal, yeah.
And while base 10 is great for, counting your sheep or your coins, it's actually pretty terrible for geometry and astronomy.
Wait, hang on. Why is 60 better than 10? My brain is so wired for base 10, it feels like the easiest number in the world to work with.
Only because you've used it your whole life. Think about it from a purely mathematical standpoint. Think about divisibility, the number 10. What can you divide it by cleanly?
2 and 5, and 1 and 10, I guess.
Right. And that's it. It's actually a very rigid number. If you try to divide a circle or a day or anything cyclical by 10, and then you need a third of that, you get 3.333 repeating. It's messy. It creates fractions all over the place.
Okay, I see what you're saying.
Now think about 60. You can divide 60 cleanly by 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. It's an incredibly flexible, elegant number.
So if you're an early astronomer trying to slice up the sky into different sectors or chart the moon's cycle against the sun's,
You want a number that can be broken into halves, thirds, quarters, fifths, sixths, without creating a mathematical mess. 60 is a godsend for that kind of work.
So it wasn't some random cultural quirk. It was a deliberate mathematical tool they chose because it was the best one for the job of measuring circles and cycles.
Precisely. And because they were the first ones to create these massive systematic records, we're talking about thousands and thousands of clay tablets listing the rising and setting of Venus, lunar eclipses, everything. Their math became the standard. They created the data format. The Greeks picked it up, the Arabs preserved and enhanced it, and eventually it ended up on your wrist.
So every time I check the time, I'm basically speaking Babylonian.
You are. You're running a piece of software that's 4,000 years old. They also gave us the 360-degree circle, which is, roughly based on the number of days in a year, but rounded slightly to fit that beautiful base 60 elegance.
That's a great way to put it, a 4,000-year-old software update. But they weren't just doing this for fun, right? The sources talk about star mapping as a way to regulate daily life. This wasn't separate from their religion, was it?
No, and that's a modern distinction we have to be careful not to project backwards. For a Babylonian priest astronomer, the planets were the gods. Marduk was Jupiter. Ishtar was Venus. So tracking their movements across the sky was a form of divination, of reading the will of the divine. But at a very practical level, it also allowed them to predict, with incredible accuracy, the annual flooding of the Tigris and Euphrates rivers. It let them know exactly when to plant the barley.
It's this perfect fusion of theology and agriculture. Survival depended on it.
Completely.
Now, speaking of that fusion, let's jump across the globe to Mesoamerica, to the Maya. Because if the Babylonians were the masters of base 60, the Maya were, without a doubt, the Venus detectives.
Their obsession with Venus is it's unparalleled in the ancient world. They calculated the synodic period of Venus, that's its cycle in the sky, which is 584 days, and they did it with an error rate of something like 2 hours over a span of 500 years.
Okay, stop right there. 2 hours. Over 500 years. How on earth do you even verify that? How do you achieve that level of precision with just the naked eye? No telescopes, no atomic clocks?
It's all about two things: architectural alignment and multi-generational data logging. They built entire structures, temples like the one at Chichen Itza, specifically designed as observatories.
So the buildings themselves were the instruments.
Exactly. On a certain day of the year, Venus would appear perfectly framed in a specific window or aligned with a particular doorway. If it appeared a little bit to the left or right of where it was supposed to be, they knew the calendar was drifting, and they would adjust the math in their codices.
That implies a level of institutional discipline and continuity that I find hard to wrap my head around.
Yeah.
We struggled to keep a public works project going for 5 years. They maintained a single data collection project for centuries.
Because it was absolutely central to their worldview, to their definition of reality itself. But what I found most compelling in the research wasn't just the raw numbers, it was the metaphors they used to encode this science. We have to talk about the Earth crocodile.
Yes. I was hoping you'd bring this up, because on the surface, this sounds like pure fantasy. The source material says the Maya believed the Earth was a giant crocodile floating in a watery underworld.
It sounds like something out of a children's storybook, I agree.
But the research argues this is actually a sophisticated meteorological model.
It is. The metaphor states that the breath of this cosmic crocodile flows out of caves. And this breath is what brings the rain. Now, if you've ever been to the Yucatan Peninsula, what's the landscape?
It's all limestone, full of caves and these deep sinkholes, the cenotes.
Exactly. It's a porous landscape. In the hot, dry season, the air pressure builds. The caves and cenotes, which are cooler and full of moisture, effectively exhale mist and cool air as the barometric pressure drops outside.
And a significant drop in barometric pressure is what precedes a major rainstorm or a hurricane.
Precisely. So when the Maya saw the caves breathing mist, they knew the rains were coming. Describing the Earth as a crocodile that breathes rain wasn't a superstition. It was a poetic, memorable description of barometric pressure differentials and their effect on a limestone karst landscape.
That's a huge takeaway for this whole conversation.
Yeah.
We tend to look at ancient myths as the opposite of science. But in this case, the myth is just a zip file for the science. It's a compression algorithm to make complex data memorable and transmissible.
It's a mnemonic device. It's a lot easier to teach your kids the crocodile is breathing, it's time to prepare the fields, than it is to teach them. The differential in barometric pressure between the subterranean and ambient environments has reached a critical threshold predictive of precipitation.
A very fair point. Okay, let's pivot now across the Pacific to China. Because while the West, and specifically the Greeks who we'll get to, had this very rigid idea of the unchanging heavens, the Chinese scholars saw something very different. They saw a sky that was dynamic.
And the ultimate example of that is the guest star.
This is guest star 185.
Yes, observed between December of 185 CE and August of 186 CE. It appeared suddenly in the sky between the constellations we now call Circinus and Centaurus. Now, for the Chinese imperial observers, this was a massive anomaly, a huge deal.
Why?
Because in the dominant Western model at the time, the Aristotelian view, the stars are fixed. They are eternal and perfect. They do not change. They don't appear or disappear.
But the Chinese records are very clear. This thing just switched on.
It switched on, and it stayed on. Today, we're almost certain it was a supernova, an exploding star, and it was so bright it remained visible to the naked eye for 8 straight months.
8 months. That's not just a passing comet or a flicker. That's a permanent feeling fixture.
Imagine looking up tonight and seeing a brand new star, as bright as Mars or Jupiter, and it just stays there for the better part of a year. It completely shattered the idea of immutable heavens and forced the Chinese astronomers to accept that things in the cosmos could be born and things could die.
And because their emperors believed their mandate of heaven to rule was directly connected to celestial events, they had an obligation to record these things meticulously.
Incredibly meticulously. We actually use their records today to help date supernova remnants that we see with modern radio telescopes. It's amazing. We can look at a giant cloud of expanding gas out in space, calculate how fast it's moving, and wind the clock back 2,000 years to see when it should have exploded. And more often than not, we check the Chinese logs for that year, and there it is. Guest star appeared in this location.
So we're fact-checking modern astrophysics using court records from the Han Dynasty.
That is the power of good, continuous data. It's timeless.
Okay, now we need to shift gears completely. We've talked about people looking up at the sky from stone pyramids and ziggurats, but what if you're looking up from a canoe in the middle of the largest ocean on the planet?
We have to talk about the Polynesians.
I feel like when we talk about the foundations of civilization, we have this bias towards stone. We think of walls, roads, temples. But the Polynesians built a civilization on water.
A liquid continent. The area we call the Polynesian Triangle is just vast. It's a section of the globe with Hawaii at the northern point, Easter Island, or Rapa Nui at the eastern point, and New Zealand, Aotearoa, at the south. It's an area larger than Russia.
And they settled this entire region without maps, at least not paper maps as we'd recognize them.
They didn't have paper maps, but they had something far more powerful in a way. They had the octopus.
Explain the octopus of the Pacific. This is another one of those metaphors that sounds like a myth, but is actually a highly sophisticated map.
It's a beautiful oral tradition, a conceptual map. It frames the entire geography of the Pacific not as a grid of latitude and longitude, but as a giant octopus. The head of the octopus is at the sacred island of Raiatea in what is now French Polynesia.
Which was a major cultural and religious hub, right?
The central hub. And from its head, the tentacles of the octopus spread out across the ocean, representing the major deep ocean sailing routes to all the other island groups. So a navigator wouldn't memorize a bearing of, say, 270 degrees. They would memorize a tentacle. Follow this tentacle to get to Tonga. Follow this other tentacle to get to the Marquesas.
You know, that completely changes the psychology of the ocean. When you look at a modern Western map, the Pacific is this terrifying, vast, empty blue space with these tiny, isolated dots of land. It makes the islands look impossibly far apart.
Exactly. It emphasizes the isolation. But the octopus metaphor implies connection. The ocean isn't the barrier. It's the connective tissue. It's the road network. The great Tongan scholar Epeli Hoafa wrote about this, calling it our Sea of Islands. He argued we shouldn't see Polynesia as islands in a far sea, but as a sea of islands. The water connects, it doesn't divide.
That cognitive shift is enormous, and this wasn't some recent development. The timeline for this exploration is incredibly deep.
Oh, it goes way back. The great Austronesian expansion starts out of Taiwan thousands and thousands of years ago. The ancestors of the Polynesians, the Lapita culture, they reached places like Tonga and Samoa by around 900 BC. They were making open ocean crossings when the ancient Greeks were still cautiously hugging the coastlines of the Mediterranean.
And speaking of the Greeks, we should probably contrast this vast, open, connected octopus network with the early European view of the cosmos. Because while the Polynesians saw an open road, the Greeks, they basically saw a ceiling.
A series of ceilings, really. The famous crystal spheres.
This is the model of the universe that dominated Western thought for over 1,000 years.
It really did. The early Greek astronomers, and this is all mathematically solidified by Ptolemy, pictured the Earth as fixed. unmoving, right at the center of everything.
The human ego, right at the center of the universe.
You could say that, yes. And surrounding the Earth were these nested, transparent spheres, like the layers of a glass onion. One sphere held the moon, the next one held Mercury, then Venus, then the sun, then Mars, and so on.
And the final, outermost sphere held all the stars.
Exactly, the fixed stars. In this model, the stars aren't trillions of miles away. They're just lights embedded in the ceiling of the universe.
So they weren't distant suns. They were just painted on the dome.
Effectively, yes. They believed the universe was small, it was compact, it was orderly, and it was perfect. The spheres rotated in perfect harmony, creating the celestial music of the spheres. It's a very tidy, almost claustrophobic universe.
It sounds safe, in a way. It makes you feel important. Everything is literally revolving around you.
It is safe, but it was also completely wrong. And clinging to that safe view held back European science for centuries because they had to invent more and more complicated mathematical kludges to explain why the planets didn't actually move the way the perfect sphere said they should.
The infamous epicycles.
The dreaded epicycles. But we'll get to how that all shattered later, because before we break the crystal spheres, we need to go back to the Pacific. There's a debate that raged about Polynesian voyaging. It got incredibly heated in the 20th century, and I think it perfectly illustrates how our own biases can blind us to scientific reality.
And that brings us perfectly to Section 2, active debate. This is where the science disagrees. And we're starting with the battle between heroism and drift.
And it really was a battle. On one side, you had what's called the heroic vision. This came from late 19th century scholars, guys like Fornander and Smith. They looked at the Polynesian Triangle and imagined these great coordinated fleets of voyagers led by warrior kings deliberately conquering the Pacific.
You give them agency. It says, we meant to do this. This was planned.
Exactly. But then, in 1956, a New Zealand historian named Andrew Sharp came along and published a book called Ancient Voyagers in the Pacific. And he essentially called that whole heroic vision a romantic myth.
He's the skeptic in this story. So what was his argument? I mean, it seems like a pretty hard position to take, to say you didn't navigate here, when people are clearly living on Hawaii and Easter Island.
Sharp's argument was that the distances were simply too great, and the technology, the canoes, and so on, was too primitive for intentional, targeted navigation. He claimed that the settlement of the Pacific was the result of accidental drift.
Accidental drift.
His theory was that basically canoes full of fishermen would get caught in a storm, they'd be blown helplessly off course, and if they were incredibly, ridiculously lucky, they might wash up on a new, uninhabited island before they all died of thirst.
So his theory was that the greatest human migration in history was just a long series of fortunate boating accidents.
That's pretty much it. He called it accidental colonization. And we have to be honest, there was a layer of implicit, if not explicit, racism in this view. It was built on the assumption that so-called primitive people couldn't possibly possess a scientific navigation system that rivaled or even exceeded European capabilities at the time.
It's an argument from incredulity. I can't figure out how they did it, therefore they must not have done it.
Precisely, and that must have been deeply insulting to the descendants of those great navigators. But here was the problem Sharp exploited. The oral traditions were fading. The guild secrets of the master navigators had been almost wiped out by colonization and new technologies. So Sharp could make this argument because there was nobody left who could stand up and say, no, you're wrong, watch me do it.
Until the 1970s.
Until the 1970s. And this is where experimental archaeology becomes something like an action movie. An anthropologist named Ben Finney, along with a group of native Hawaiians and other scholars, founded the Polynesian Voyaging Society.
And their plan was to settle the debate once and for all.
Yes. They decided the only way to prove Sharp wrong was to build a boat. A full-scale replica of a traditional voyaging canoe.
Bakukulia.
The Hotilia, a performance-accurate, double-hulled canoe. No screws, no nails, everything lashed together with miles of rope, just like the ancestors did it. And their plan was to sail it from Hawaii to Tahiti.
That's, what, over 2,000 miles of open ocean?
Over 2,000 miles. And the rules were incredibly strict. No GPS, no compass, no sextant, no charts, no modern instruments of any kind. But they had a huge problem. They had the canoe, but they didn't have a navigator. The knowledge of how to make that specific journey had been lost in Hawaii for generations.
So what did they do? Where did they find someone?
They had to search the Pacific, and they found Mau Pialuk. He was a master navigator, a pu, from a tiny atoll in Micronesia called Setawal, one of the last places on Earth where this knowledge was still being passed down in an unbroken line. He didn't speak English. He couldn't read a map, but he could read the stars in the ocean better than anyone alive, and he agreed to guide them.
I can't even imagine the pressure on that voyage, the weight of proving your ancestors right.
The pressure was immense. There were cultural clashes on board, physical exhaustion, but Mao navigated. He just sat on the deck day and night, watching the stars rise and set, feeling the rhythm of the ocean swells through the hull of the canoe, barely sleeping for a month. And I want you to just imagine the moment. After 30 days of seeing nothing but blue water in every direction, Mao quietly tells the captain, "Tahiti will be there tomorrow."
And was it?
It was. Dead on. They sailed into Papeete Harbor in Tahiti, and something like 17,000 people, half the island's population, came out to greet them. It was a massive cultural renaissance. But scientifically, it was a knockout blow. It killed the drift theory dead. You can't drift from Hawaii to Tahiti. The winds and currents are against you. You have to aim. You have to navigate with intent.
It proves the science was real.
It proved the science was real, and the ancestors were heroes, not victims of chance.
But there is another debate that is still very much alive. And this one is even more controversial because it doesn't just rewrite Pacific history, it rewrites the history of the Americas.
Yeah.
The big question, did the Polynesians keep going? Did they make it all the way to South America?
This is the pre-Columbian contact debate, and it is absolutely fascinating because it's being fought right now with ancient DNA, with linguistics, with archaeology.
Okay, let's look at the evidence. Exhibit A has to be the sweet potato.
The kumara. This is the botanical smoking gun. Sweet potatoes are native to the Andes region of South America, period. They do not grow naturally anywhere in the Pacific Islands. And yet, when European explorers like Captain Cook arrived in the 18th century, they found sweet potatoes being cultivated everywhere, from New Zealand to Hawaii. And we now have archaeological evidence that dates the sweet potato's presence in the Cook Islands to at least 1000 CE.
So, nearly 500 years before Columbus, you have a South American plant thriving in the middle of the Pacific.
Exactly. Now, there are only two ways that could have happened. Theory one, the seeds floated. They got washed out to sea, floated for thousands of miles, and washed up on a beach. The biological dispersal argument.
Is that plausible?
It's possible, but very, very unlikely. Sweet potato seeds don't fare well in salt water for that long. But the real clincher is the linguistics. In Quechua, the language of the Andes, one of the words for sweet potato is kumar or kumara.
And in Polynesian languages?
The word is kumara.
Okay, a seed floating across the ocean is one thing. A word floating across the ocean is something else entirely. That implies two people were standing next to each other. One of them pointed.
It implies human contact. It implies a Polynesian canoe landed in South America. They saw this new food, asked, "What do you call this?" We're told, "Kumara," and then they sailed back home with both the plant and the name.
That feels pretty convincing. But then you have Exhibit B, which is the chicken bones. And this is where the story gets really messy.
Oh, it gets very messy. So in 2007, a major study came out. Researchers had analyzed chicken bones found at an archaeological site in Chile called El Arenal. These bones were carbon dated to the 1300s, well before the Spanish arrived.
And chickens are not native to the Americas. They come from Southeast Asia.
Correct. So if there are pre-Columbian chickens in Chile, the only plausible way they got there is on a Polynesian canoe. And the 2007 study was explosive because they claimed the ancient DNA from these bones was a perfect match for rare chicken breeds found in Tonga and Samoa.
Case closed, right? Final proof.
That's what everyone thought. But science is all about replication and peer review. A few years later, a different team of scientists reanalyzed data and argued that the specific DNA sequence they found wasn't just Polynesian, it was also common in some European chicken breeds. They suggested the original sample might have been contaminated with modern DNA in the lab, or that the dating was wrong.
Contamination is a huge problem in ancient DNA work, isn't it? I mean, if a researcher eats a chicken sandwich for lunch and then handles the ancient bone,
you've potentially ruined the sample.
Yeah.
Exactly. Modern chicken DNA is everywhere. So the chicken bone debate is currently at a stalemate. The original authors stand by their work and have published rebuttals while the critics maintain their doubts. But when you layer the chickens on top of the sweet potatoes and then you add in other things.
like the canoe designs.
Right. The Tomalo canoes of the Chumash people in Southern California. They're built using a sewn plank technique that is found all over Polynesia but is virtually unknown elsewhere in native North America. The evidence keeps piling up that the Pacific was a two-way street.
It just shows that history is so much messier and more interconnected than the neat chapters in our textbooks would have us believe.
Borders are a modern obsession. For ancient peoples, the ocean was a highway.
Okay, speaking of messy history, let's tackle one more major debate in this section. The very idea of the Dark Ages in Europe. We have this popular Eurocentric story that after the fall of Rome, science basically went to sleep for 500 or 600 years.
A narrative that is only true if you completely ignore the rest of the planet. While Europe was certainly going through a period of fragmentation and struggle, the Islamic world was exploding into its golden age. From the 7th century all the way to the 16th, cities like Baghdad, Damascus, and Cordoba in Spain were the undisputed intellectual centers of the world.
And the debate here often revolves around the relationship between religion and science. The common narrative is that religion hinders science. Galileo versus the church is the classic example. But in the Islamic Golden Age, the argument from the sources is that religion actually drove the science.
It absolutely did. It all comes down to the need for precision.
Break that down for us. Why did the practice of Islam create a need for world-class astronomy?
There are two main practical religious reasons. The first is the Qibla. Every Muslim is required to pray facing the direction of the Kaaba in Mecca. Now, if you're in Damascus, that's fairly straightforward. But if you're in Spain or Morocco or India, calculating the precise direction to Mecca across the curve of the Earth is an incredibly complex problem in spherical trigonometry.
You can't just guess. Mecca is sort of that way.
Not if you're a devout scholar or architect. You need the exact angle. The second reason is the prayer times. The 5 daily prayers are determined by the position of the sun: dawn, noon, afternoon, sunset, and nightfall. And of course, those times change every single day of the year, depending on your latitude and the season.
So every major mosque needed essentially a resident astronomer to calculate this stuff.
They did. They created a specific role called the muwaqwit, the official timekeeper. These religious requirements acted like a massive government grant for scientific research. It poured money and brain power into astronomy. It drove the invention of better instruments like the astrolabe and the quadrant, and it spurred huge advances in mathematics, especially algebra and trigonometry, which were needed to do the calculations.
So instead of suppressing scientific inquiry, the faith acted as a massive R&D fund.
Without a doubt. Many Quranic verses, like the ones mentioning celestial bodies swimming in an orbit, were interpreted as a divine instruction to study the heavens.
So the big question then is, why did it stop? Why isn't the Middle East the center of the global space race today?
That's the million-dollar decline debate. It's incredibly complex with no single answer. A major factor was the Mongol invasion in 1258. The sack of Baghdad was a cataclysmic event. The stories say they destroyed the House of Wisdom and threw so many books into the Tigris River that the water ran black with ink.
A physical destruction of knowledge.
A catastrophic one. Then you also have long-term shifts in political patronage. As the unified caliphate fragmented into smaller, competing states, the centralized funding for massive scientific projects like observatories began to dry up. It's a stark lesson in how fragile a scientific ecosystem is. It needs peace, stability, and money to thrive.
A sobering thought. Let's move on to section 3. Frontiers. This is where we get into the tech, the actual tools, both physical and mental, that made all of this incredible science possible.
The toolkit of the ancients. I love this part.
Let's start with the hardware, the physical gadgets. You called the astrolabe the smartphone of the medieval world. Paint a picture of this thing for us. If I'm holding an Islamic Golden Age astrolabe, what does it look like? What does it do?
It is a thing of beauty. Imagine a heavy, solid brass disc, maybe the size of a modern tablet or a bit smaller. It's covered in these incredibly intricate, precise engravings. It has a main body, the mater, and then you can slot in different plates called tympans that are designed for different latitudes.
So it's customizable for your location.
Exactly. And on top of that, you have this beautiful cutout web-like disc called the rete, which is essentially a star map. The points on the web represent the positions of the brightest stars.
And the parts move.
Yes, the rete rotates over the plate. And by aligning the star map with the lines on the plate, based on the current position of the sun or a known star, you can basically create a model of the entire sky at that exact moment. You can use it to tell the time, day or night. You can find your latitude. You can determine the height of a building. You can survey land. You could even cast a horoscope. It was a graphical computer, a clock, a GPS, and a calculator, all in one handheld device.
So if you were a scholar, a merchant, or a ship's captain in the 12th century, you had to have one.
It was the essential piece of kit. It was the mark of a truly educated person.
But sometimes a handheld device just wasn't powerful enough. We have to talk about Ulu Beg's observatory in Samarkand. The scale of this place is it's hard to even visualize.
Ulu Beg was a Timurid sultan in the 15th century. He was a ruler, but his real passion was astronomy. He understood a fundamental principle of measurement. Small instruments have small errors, but if you want to eliminate error, you have to make the instrument huge.
And when you say huge, how huge are we talking?
He built what's called a Fokker sextant. It's a device for measuring the angle of stars above the horizon. But instead of being handheld, it was a massive trench dug into the earth, lined with marble. The instrument had a radius of 40 meters, that's over 130 feet. It was essentially a 3-story building that functioned as a single protractor.
Why? What does that sheer size give you in terms of data quality?
Resolution. Precision. On a small handheld sextant, 1 degree of arc might be less than an inch wide, making it hard to read fine measurements. On Ulugh giant marble arc, a single degree was enormous. He could mark off minutes and even seconds of arc with incredible accuracy. This is what allowed him to produce his star catalogue, the Zigi Sultani, in 1437.
And how good was that catalog?
It was the most precise and comprehensive star catalogue produced anywhere in the world, and it wasn't surpassed in accuracy until the invention of the telescope more than 150 years later. He corrected fundamental errors in Ptolemy's ancient data that had been accepted as fact for 1,000 years, simply because his ruler was bigger and better.
That's the hardware. But now I want to switch back to the Polynesians for the software, because we've established they didn't have astrolabes or giant marble sextants. Their technology was, as the sources say, sensory technology.
This is, for me, the most mind-blowing part of the whole story, because it demonstrates the incredible capacity of the human brain to be the primary instrument, to process environmental data without a screen or a dial.
Okay, let's break down this non-instrumental toolkit. Let's start with the star compass. This isn't a physical object you hold, right?
No, not at all. It's a mental construct. It's a system that the navigator memorizes and projects onto the 360-degree horizon around the canoe. The navigator memorizes the precise rising and setting points of about 32 key stars or constellations. These points divide the horizon into houses or directions.
So they're literally looking at the horizon and seeing this invisible grid overlaid on it.
Exactly. And they use this for a brilliant technique called sailing down the latitude. Let's say you're in Tahiti and you want to sail to Hawaii. You know from oral tradition that a specific star, let's call it a zenith star, passes directly over Hawaii every single night.
Okay.
So you don't aim the canoe directly at Hawaii. That's too hard. It's a tiny target. Instead, you just sail north. You keep sailing north until you observe that specific zenith star passing directly over your head through the mast of your canoe.
At which point you know you're on the same latitude as Hawaii?
Precisely. And then you simply turn the canoe due west and you run down the latitude, keeping that star in the same position until you literally run into the Hawaiian Islands. It turns a difficult 2-dimensional search problem into a much simpler 1-dimensional one. It's genius.
That's incredible. But that system relies on seeing the stars. What happens on a cloudy night? Or during the day? You can't just stop.
No, you can't. That's when you switch to your other instruments. You use the ocean itself. This is wave piloting.
This is the one that really gets me. The idea of feeling the direction of the swells.
Think of it this way. Imagine you're in a perfectly still swimming pool with your eyes closed. If someone gently starts making waves at the far end, you'll feel that consistent rhythmic pulse hit you. That's an ocean swell, generated by trade winds thousands of miles away. It's incredibly regular and reliable.
Okay, I can picture that.
Now imagine there's a big inflatable island toy floating in the middle of the pool. When that regular swell hits the toy, what happens? It gets disrupted. The waves will bounce off it, bend around it. It creates a confused pattern.
So the island is the inflatable toy.
The island is the toy. It's a giant object that creates a shadow in the swell pattern. A master navigator can lie down in the hull of the canoe, close their eyes to heighten their other senses, and literally feel the subtle changes in the rhythm of the canoe rising and falling. They can distinguish the deep, primary swell from the reflected chop bouncing off an island that's still 100 miles away, far below the horizon. They can feel land long before anyone can see it.
That is an almost superhuman level of sensory attunement.
It's not superhuman. It's just what the human body is capable of when it's trained from childhood to pay exquisite attention to the environment.
And then there's Tilapa. The sources call it underwater lightning. I need you to try and explain this because it sounds like pure magic.
It does sound like magic, but there's likely a scientific explanation. Navigators describe it as faint, rapid streaks or flashes of light deep underwater that seem to radiate outward from islands. They say it's best seen at night, when you're roughly 80 to 100 miles away from land. It's like a compass needle made of faint light, pointing you home.
What could that possibly be? Is it bioluminescence?
That's the leading theory, though it's still not fully understood by Western science. The idea is that it's bioluminescent plankton being agitated by complex wave interference patterns. The deep ocean swell hits the submerged slopes of an island or atoll, it bounces back, and it interferes with the incoming swells, creating a unique turbulence pattern that makes the plankton light up. The navigators learned to read these light patterns as a homing beacon in the pitch dark.
Stars, waves, underwater light. And then finally, there are the birds, the shore-sighting bird.
The frigate bird, specifically. This is a crucial piece of data. The frigate bird is a large seabird, but it has a fatal flaw. Its feathers are not waterproof. It doesn't have the natural oils that a duck or a seagull has. If it lands on the surface of the ocean, it gets waterlogged, can't take off again, and it drowns.
Which means it absolutely has to roost on land every single night.
Every single night. It can fly for hundreds of miles during the day to hunt for fish, but it must return to land before dusk. So if you're a navigator out at sea and you see a frigate bird in the morning, you know which direction it's flying away from. That's the direction of land. If you see one in the late afternoon, it will be flying purposefully toward land. Its range is about a day's flight. If you see one, you know land is close. All you have to do is follow the bird.
It's this beautiful, comprehensive, redundant system. If the stars are clouded over, you read the waves. If the waves are confusing, you look for the birds or the light. Every part of the environment is a piece of data.
They were processing a multivariable environmental input in real time using the most powerful computer we know of, the human brain. It makes our total reliance on a single GPS signal look a little fragile, doesn't it?
It really does. We're lost if our battery dies. They found a 1-mile-wide atoll in the middle of a 10 million square mile ocean.
Which brings us full circle back to Europe and the great European paradigm shift, because eventually Europe started getting better data too. And that new, better data completely broke their cozy crystal universe.
We're talking about the seismic shift from the crystal spheres to modern physics. And the story really starts with a man named Tycho Brahe.
The great data collector. Tycho is one of the most incredible characters in the history of science. He was a Danish nobleman who famously lost part of his nose in a sword duel over a mathematical formula and wore a prosthetic made of brass. He also had a pet moose that, according to his letters, died after falling down some stairs when it drank too much beer at a dinner party.
Wait, seriously? The moose story is real?
Oh, it's real. He was a larger-than-life figure, but he was also a meticulous, obsessive genius. He realized that all the old astronomical tables from Ptolemy onward were full of errors. So he convinced the king of Denmark to give him an entire island where he built the world's most advanced observatory, Uraniborg. And he spent decades just recording data, the position of the planets, every single night without fail.
He was the ultimate log taker. No theories, just raw data.
He was, and his data did something revolutionary. He observed a great comet in 1577 and, using parallax, was able to prove that it was moving far beyond the moon. It was passing through the supposed crystalline spheres of the planets. If the spheres were solid crystal, the comet would have shattered them.
So his data proved the heavens weren't solid, they were empty space.
Exactly. It shattered the physical reality of the spheres. But he was still a product of his time. He couldn't quite bring himself to let go of the idea that the Earth was the center. He came up with this weird, complicated hybrid model. But his brilliant, long-suffering assistant, Johannes Kepler, didn't have that same mental block.
Kepler, the analyst.
Kepler inherited Tycho's mountains of data after Tycho's death. Specifically, the incredibly precise data on the movement of Mars. And he tried for years to make that data fit the universally accepted theory that planets moved in perfect circles.
Because circles were seen as the perfect divine shape. God wouldn't use a messy shape.
That was the philosophical and religious belief. But the data just wouldn't fit. No matter how he tweaked the model, Mars kept drifting off the predicted circular path. It was a crisis of faith for him. Finally, in desperation, he threw out the circle and tried a different shape. An ellipse. A simple oval. And click. It fit perfectly. The math worked. But to accept that, he had to destroy 2,000 years of dogma. He had to accept that the universe wasn't built on perfect circles. He had to prove that planets move in these slightly squashed ovals and that they speed up and slow down as they go.
That is the moment modern physics is born, isn't it? When the observational data is finally allowed to override the philosophical dogma.
That is the exact moment. And then, of course, Copernicus and later Galileo sealed the deal by taking the Earth out of the center and putting the sun there instead.
Which elegantly solved the whole retrograde motion problem.
Right. For centuries, astronomers had struggled to explain why planets like Mars sometimes appear to stop, moves backward in the sky for a few weeks, and then move forward again. The old system needed these absurdly complex epicycles, little circles spinning on bigger circles, to account for it. The new heliocentric model had a beautifully simple explanation.
We're just lapping them on an inside track.
Exactly. When Earth, in its faster inner orbit, overtakes Mars, Mars appears to move backward relative to the background stars, just like a collier passing on the highway seems to move backward relative to you for a moment. It's an illusion of perspective.
Simple, elegant, and correct. What a journey. We've gone from a crocodile breathing rain in a cave to an elliptical orbit governed by the laws of physics.
It's the whole story of science, in a way.
Okay, let's move into our final section, implications. Why does all of this ancient history matter today? Is this just interesting trivia, or does it have a real impact on our world?
Oh, it's definitely not just trivia. Let's start with the hard-nosed economics of navigation.
Trade routes.
Absolutely. The incredible advancements in astronomy and mathematics in the Islamic world weren't just for calculating prayer times. They directly enabled Muslim merchants and sailors to dominate the trade routes of the Red Sea, the Mediterranean, and all across the Indian Ocean for centuries. If you can navigate more accurately than your competitors, you can trade farther, faster, and with less risk. Navigation was the engine of economic supremacy.
It's the same today, really. Whoever controls the GPS satellite network effectively controls the arteries of the global economy.
Precisely. And for the Polynesians, the economics were even more fundamental. It wasn't about profit. It was about resource scarcity.
Right. Island hopping sounds like a fun vacation. But the reality was that it was a necessary solution to overpopulation and resource depletion. A small island can only support so many people. When the taro patches were full and the fish stocks were getting thin, you had to find a new island. Navigation wasn't a choice. It was the essential technology for survival and expansion. There's also the massive implication here about knowledge preservation and loss.
This is so crucial. The Polynesian navigation system was an oral tradition. It was a guild secret, passed down from master to apprentice. It wasn't written in books. So when Europeans arrived with their new technologies, magnetic compasses, sextants, paper charts, and imposed their own systems, the oral tradition was seen as obsolete and was nearly lost forever.
Which is why the Hukulia voyage wasn't just a scientific experiment, it was a cultural resurrection.
It was an act of decolonizing navigation. It was a powerful statement that this indigenous science was valid, it was robust, and it was brilliant. It was about reclaiming a heritage that had been dismissed as primitive superstition or accidental drift.
And on the other side of the world, we can't forget the Islamic role in transmission.
No, absolutely not. During Europe's early medieval period, when many of the classical Greek texts of Ptolemy and Aristotle had been lost or forgotten, it was Muslim scholars who sought them out, translated them into Arabic, studied them, critiqued them, and improved upon them with their own discoveries in algebra and trigonometry.
And then they passed that knowledge back to Europe.
Through centers of learning in Spain and Sicily, yes. Without that intellectual bridge, that preservation and transmission of knowledge, the European Renaissance might have been delayed by centuries or might not have happened in the same way at all.
So that leads to a bigger societal and philosophical impact. I was struck by this idea of meaning versus mechanics.
Unpack that a little.
Well, it seems that for most of the ancient cultures we've discussed, astronomy was primarily about meaning. The questions were, why are we here? What is our destiny? What do the movements of the gods mean for our kingdom? The sky was a source of purpose.
And modern science is focused almost entirely on mechanics. How does gravity work? What is the chemical composition of that star? How fast is the universe expanding?
Exactly. But the sources seem to suggest that, at our core, we're still doing what the ancients did. Whether we're using the James Webb Space Telescope to look back to the dawn of time, or the Maya were using a temple alignment to track Venus, we're still just trying to find our place in the cosmos. We're trying to orient ourselves in the grand scheme of things.
I completely agree. We're still looking up and asking that same fundamental question, where do we fit into all of this? The tools have changed, but the quest is the same.
And that quest for navigation is so deeply tied to independence and freedom.
There's that wonderful, touching story in the notes about a modern Lapita expedition. They sailed a traditional canoe to the island of Tikopia, which had become isolated because a cyclone had wiped out the specific trees they needed to build their own voyaging canoes. They were trapped.
And the expedition gifted them new canoes.
Yes, they gifted them the tools to end their isolation. Navigation is freedom. It's the ability to connect, to move, to not be trapped.
So when we wrap this all up, what is the modern legacy of all this ancient knowledge?
It's all around us, hiding in plain sight. We still use the Babylonian base 60 system every single second of every day. A huge number of the named stars in the sky still have their Arabic names. Aldebaran, Betelgeuse, Rigel, Vega. That's a direct legacy of the Islamic Golden Age.
And, as you mentioned with GPS, the old ways are not obsolete. The U.S. Naval Academy still teaches every midshipman celestial navigation with a sextant.
They absolutely do. Because in a world of potential GPS jamming, cyber warfare, or satellite failure, the stars are the ultimate unhackable backup system. You can't turn them off. They are the most reliable navigation grid we have.
And I think I'll carry with me that idea of the grand octopus.
The Polynesian metaphor. It's such a powerful way to reimagine the world, not as land masses separated by barriers of water, but as a single connected entity. I think that's a legacy, a way of thinking we desperately need today. In our globalized but often polarized world, we need to focus on the tentacles that connect us, not the empty spaces that seem to separate us.
A beautiful thought to end on. The ocean connects us, and the sky connects us all.
Indeed.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
We certainly are.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content. And support us in Patreon. Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.